What does an action mean before anyone names it? In familiar software, the answer is usually hidden in the code. A button moves, rotates, opens, selects, or deletes because a designer defined it that way. But general intelligence cannot rely on labels arriving first. It must enter an unfamiliar world, interact, observe the consequences, and build meaning from evidence. This is the central idea behind action semantic inference in ASRA, the adaptive scientific reasoning architecture. Many modern AI systems assume that the meaning of an action is already known. The policy chooses from a fixed menu, the environment gives clean feedback, and the training loop rewards the right mapping. That is powerful when the world is stable. But it is fragile when the mechanics are hidden, the objective is implicit, or the same action changes its effect across contexts. Imagine an agent dropped into an ARC-style grid world. It sees a state. It can choose Action 1, Action 2, Action 3, or Action 4. But those labels are empty. They do not say move, push, toggle, destroy, swap, or wait. The agent has to turn anonymous interactions into grounded concepts. Action semantic inference is the process of learning what actions do, under what conditions they work, what state transitions they cause, what hidden mechanics they imply, and how those mechanics relate to a goal. The system does not begin with semantics. It constructs semantics from transitions. The first experiment is simple. The agent tries Action 1. The colored object moves upward by 1 cell. ASRA does not immediately declare that the action means up. It records a transition, highlights the changed cells, computes the difference map, and forms a provisional semantic hypothesis. When Action 1 is tested again in a compatible context, the same upward motion repeats. Consistency matters. ASRA updates confidence because the evidence now points toward a stable relation between the action, the object, and the spatial change. Meaning begins as a statistical pattern, then becomes a usable abstraction. Next, Action 2 moves the object right. The hypothesis graph begins to organize actions by effect. Action 1 clusters near upward translation. Action 2 clusters near rightward translation. The agent is no longer just reacting. It is building a vocabulary of interaction. Then Action 3 appears to do nothing. A weaker system may treat this as failure. ASRA treats it as information. No visible change may mean the action is invalid here, its effect is hidden, or the required context is missing. Uncertainty is not ignored. It becomes a target for exploration. When the agent moves near an obstacle and tries Action 3 again, the obstacle disappears. The action was not meaningless. It was conditional. Its semantics emerge only in the right environmental relation. This is crucial. ASRA must infer not only effects, but the contexts that activate those effects. The first mechanism is state differencing. ASRA compares the previous state to the current state and asks what changed. Which cells moved? Which regions transformed? Did topology shift? Did a color, boundary, obstacle, or relation change? This turns raw observation into a structured delta. From these deltas, ASRA forms semantic hypotheses. Action 1 is likely move up. Action 2 is likely move right. Action 3 is not simply no up. It is closer to conditional destroy. The system does not hardcode the interpretation. It maintains competing explanations and updates them as new evidence arrives. ASRA does not explore randomly forever. It chooses experiments that reduce uncertainty. If an action is ambiguous, the agent searches for contexts where the ambiguity can collapse. It varies position, object relation, obstacle proximity, and sequence. The policy becomes a miniature scientific method. Action semantics are causal, not just correlational. ASRA tries to infer rules of the form: if action A is executed in context C, effect E occurs. The same action can move, fail, transform, or reveal a hidden mechanic depending on the state. Meaning lies in the relation between action and context. Once a semantic pattern becomes reliable, ASRA stores it as memory. Move up, move right, conditional destroy, context-gated interaction. These are not isolated observations. They become reusable abstractions. In a new environment, memory can propose priors while exploration tests whether those priors still hold. Over time, actions can be represented in a latent semantic space. Actions with similar effects move closer together. Actions with conditional behavior form separate clusters. This geometry lets the system reason beyond the original labels and compare actions by what they do. Most systems fail here because they memorize action to outcome mappings without understanding the mechanism. A reward signal can train behavior, but it does not necessarily reveal why an interaction worked. When the environment changes, the memorized policy can collapse because it never grounded the action semantically. There is a biological analogy. Cells do not receive a dictionary that explains every signal in advance. They infer meaning through interaction, feedback, and environmental context. Signals become meaningful because they reliably change behavior, state, or future response. ASRA applies a similar logic to artificial agents. Technically, this system can be visualized through transition probability matrices, entropy reduction, causal graphs, semantic embeddings, and exploration trees. But the purpose of the math is simple: decide which actions have stable effects, which depend on context, and which experiments will teach the most. The payoff appears when the agent enters a new world. It may not know whether action 1 still means upward movement, but it has a grounded hypothesis and a test strategy. Prior semantics accelerate adaptation without replacing evidence. Memory becomes a guide, not a blind assumption. This matters for general intelligence because the real world rarely announces its action space. Robots must discover affordances. Scientific agents must test interventions. Adaptive systems must infer hidden dynamics. Intelligence is not only selecting an action. It is discovering what actions mean in the first place. The ASRA loop is therefore active and constructive. Act, observe, difference the states, form a hypothesis, explore the uncertain contexts, store abstractions when evidence becomes reliable. This loop turns anonymous action labels into semantic machinery. True intelligence is not knowing actions in advance. It is discovering meaning through interaction. ASRA treats reasoning as an active scientific process, where semantics are not given, but discovered. Action semantic inference is one step toward agents that do not merely execute instructions, but learn the structure of the worlds they enter. Learning meaning through interaction.